All right, so this week we're going to start looking at Unit 2. We're going to spend 2 weeks on Unit 2. The third week's going to be your assessments. There's a couple of things that we're going to get into this week. So first off, we're going to talk about IP addresses, routers, and redundancy. We're also going to start practicing for your FRQ responses that you'll have to do for the final in this class and the AP exam in May. So there's two different lecture videos. This one is just going to cover IP addresses, routers, and redundancy. So for this, you're going to have some Cornell notes that you're going to have to do. It covers lessons 3 and lessons 4 from code.org. So as I go through this information, you're going to want to answer those Cornell notes. There is an MCQ practice for this one. I think it's 12 questions, so you're going to want to log into the College Board to get those questions done. So you'll be turning in a copy of your Cornell notes, a screenshot of your completed MCQ practice from the College Board, and then there is a separate video that's going to explain the FRQ practice. That's your third assignment. So kind of getting into this, looking at Unit 2. So when we were doing Unit 1, we were talking about bits and binary and how we take analog information and we can create and store that digitally so we can use it on computers. This unit is specifically on the internet, so we start talking about how we send this information from one destination to the other, right? From one phone to another phone, from one computer to another computer. So we're going to start off by talking about protocols. So understand, when the internet was first coming about, we as a society kind of realized that we needed rules that everyone would follow, right? The idea that maybe one organization wanted to send and receive information in one way and a second organization wanted to send and receive it in a different way wasn't going to work. So we created these organizations that came together and created rules. So when we talk about these rules, we call them protocols. All right, so a protocol is just an agreed upon set of rules that specify the behavior of a system. So this unit is going to have a lot of protocols that you need to know. This unit as a whole has a lot of terms and definitions. It's really heavy on that side, so just kind of be ready for that. Spend some time on these Cornell notes and kind of memorize what these things are. So first we're going to talk about IP address and internet protocol. All right, so IP address is just the unique number assigned to each device on the internet. Internet protocol, or IP, that's the protocol or the rules that we use for sending data across the internet. The idea behind this is we are going to assign an IP address to every device that connects to the internet. You can think about this as the address that you put on an envelope, right? If I'm going to send you an envelope, I need to put your name, your street number, your street name, the city, state, and zip code. I then put that in the mailbox and a mail courier picks it up. Using that information, they look at the zip code and they say, okay, I need to send this to this post office, right? It's in this zip code. Once that post office gets it, they're going to say, okay, this is going to Temecula, so I now need to route that to the Temecula post office. And then from there, they will separate the mail out based on the street that you live to say this courier is going to deliver these envelopes and these couriers are going to deliver those other envelopes. This IP address works the same, right? So an IP address, it's these, 8 numbers that you see here, like, 122.64.18.12, something. A couple of things to notice. There is 4 numbers here essentially, right? 12, 18, 64, 122. Each one of these numbers is 1 byte or 8 bits. The largest number I could create is 255. Right? So the largest IP I could have is 255.255.255.255. Again, this is just that bits and binary. There's 8 bits for each number. If it's 8 bits, I can create 256 unique values, being the numbers 0 through 255. Right? That's where the 255 comes from. It's the largest number I can create with 8 bits. We don't go into the details on this. Just know that this kind of works the same way as that mailing address. So these numbers tell the internet, right? Tell the routers and servers on the internet where to forward this information to next. So it starts kind of looking globally, and then it works its way into your network and then your actual device on that network. Right, that is an IP address. The internet protocol, that is the set of rules for sending data across the internet. So this specifies specifically how these numbers get generated and how we use them. Right, so you need to know that there is an internet protocol. There's these rules for how we send this data. The IP address is that unique number that gets assigned to each device on the internet. One thing to kind of know going into this, we've been using IPv4 forever. This is a 32-bit system. These numbers that you see, that IP address that I just typed, that is a 32-bit IP address. The problem with that is we are concerned that there are not enough IP addresses that can be created for every device that wants to connect to the internet. Right now, we're okay, but in a couple of years, we are going to run out of unique addresses that we can create using this 32-bit system. So for a couple of years now, we've been moving to IPv6. IPv6 is 128 bits, so it exponentially goes up in regards to how many bits we could use, right? It's like 2 to the 96th power, that many more bits. So that many more addresses that we can create. Coincidentally, with IPv6, we could create a unique address for every grain of sand on Earth. Right, so once we finish moving over to IPv6, we're going to be good for a long time. But we do need to make this conversion. They will kind of ask you about that on the AP exam sometimes. So just understand there's the v4 and a v6. The v6 allows for a lot more addresses. So with this, right, protocols, IP addresses, internet protocol, it gets into two more terms that you kind of have to know. One is addressing. That just kind of covers what I've been talking about, right? This idea that there's a system for assigning unique identifiers or IP addresses to devices so messages can be delivered to their destination, right? That is just addressing. There's also this idea of scalability, which is the ability of the system to grow and handle an increasing number of devices or users on the internet without breaking. So scalability is our main driving factor behind IPv4 and IPv6. We need this to scale so it can handle more. All of that kind of gets you into the idea of DNS. Right? So DNS stands for Domain Name Server. And all this really is, we know things like Google.com. Right, Apple.com. These domain names, these are good for us, right? As humans, we can memorize Google.com. As humans, we can memorize Apple.com. Computers don't actually use these. What they do is they have something called a domain name server. The job of this domain name server is to create a table, and inside of that table they have a link between, okay, this Google.com is actually for, this IP address. So that domain name server, when you make a request on the internet, hey, I want to go to Google.com, it actually first contacts a domain name server. That domain name server figures out, okay, Google.com is actually this IP address. This is what your computer is using to route that information and to get you that website. All right, the job of the domain name server is just to store these relationships. So I'm not going to go into too much more detail on that. What you do need to do is watch this video. There's a link on the details page on Canvas. They go into and kind of graphically show you how this DNS works with these servers. All right, so make sure you understand protocol, the rules, what an IP address is, this internet protocol, which is a set of rules for creating these IP addresses, the idea of addressing, and the idea of scalability. All right, this is all important because, devices on the internet, they need a unique address in order to communicate, right? We need to be able to send that message and make sure that it gets to the correct device without confusion, without failed communication. We need to make sure it gets there, right? So why do devices on the internet need these IP addresses and this IP protocol? It's so that we can make sure that the messages could be sent to the correct device at the correct time, right? As far as, what is a protocol and why must internet protocols be shared and agreed upon? Protocol is a shared set of rules for communicating on the internet, right? Internet protocols must be open and agreed upon so that all devices, regardless of the manufacturer or the location, can communicate with one another using the same standards. So this stuff that I'm talking about, this is used globally. It's not just a US thing. Everybody in the world is using these to communicate. The internet protocol basically attaches an IP address to data so that routers know where the data is coming from and where it needs to go, right? This is why we have internet protocol and why it uses IP addresses to send data to the correct destination. All right, these internet protocols attach that IP address so data can be sent through routers and go where it needs to go. So as far as why would the internet fail without these, basically if addressing rules were secret or inconsistent, devices would not know how to send data across the internet correctly. The internet would fall apart, right? That is basically lesson 3. Lesson 4 gets into routing and redundancy. So when we're talking about messages being sent and using IP addresses and using DNS servers, you need to know that there is hardware throughout the world that helps us do this. One of the devices that we use is something called a router. A router is a type of computer that forwards data across the internet. So if I'm, sitting over here and I need to get information over here, there's all these routers that my data is going to go through. I have no control over what direction it's sent, which router it goes to. It could be a super efficient path. It could be an inefficient path, right? I just make the request. So my computer sends it here. This computer's like, okay, I know the next step. I'm going to send it here. This guy's like, hey, I'm going to send you over to here. And then this guy's like, hey, I know where that is. I'm going to send it here, right? The router's job is to forward that data to the next router, to the next router, to the next router, until it reaches its final destination. The idea of routing, right? So we have routers. Those are physical hardware. Those are physical devices that do this. Routing is just this process of selecting paths that data packets take as they travel across the network, right? So routing is just this idea that it's going to go through multiple routers to get where it needs to go. The path, that is the sequence of directly connected devices that data travels through to reach its destination. So in this situation, my path is these orange lines. All right, now obviously it would have been quicker to go from here to here to here. But that's just not how it works. We have these routers, they're all connected. Some are connected to, some are connected to others, but globally we can get from point A to point B wherever it is using these routers, this idea of routing and this idea of paths. Redundancy, that's the inclusion of extra connections or paths in a network so communication can continue if something fails, right? Like, maybe this device is not working, right? For some reason it's gone down. If all I had was this one path to get from A to B, I would be in trouble, right? Because this step C would be broken. It could not connect over here. But the idea that I have multiple routers that can all get over here, that is redundancy, right? This inclusion of extra components so that a system can continue to work even if individual components fail. And this whole idea of routers and redundancy leads into fault tolerance, right? The idea of fault tolerance is that a system can continue to function even in the event of individual components failing, Right? So we want to build fault tolerance into our system. We want to have more routers than we need. More routers gives us more redundancy. Redundancy leads to fault tolerance. Right? So for your questions, what role do routers play in moving data across the internet? The routers receive data packets and forward them towards their destination. Right? That's all the router does. It gets information, sees where it needs to go next, and forwards it. Why can data take different paths through a network and still reach the same destination? This is because the internet has many interconnected routes. Routers can send packets along different paths depending on availability, traffic, failures. So again, maybe it's even this one didn't go down. It's just super busy right now for some reason. So this guy decides, hey, this guy's too busy, I'm going to send it down here. Again, redundancy, fault tolerance, all meaning our data is going to get there, right? It doesn't mean it's always going to take the same path, but it is going to get there. So this all basically makes the internet more reliable and more fault tolerant, right? Redundancy provides multiple paths for data to travel. If one path fails, the router can send data along a different path, right? That is redundancy and that is fault tolerance. Again, why is this important? It's because we don't want failures, but we know they're going to happen, right? Failures are common in large networks. Devices are going to go down. Things are going to happen. We need redundancy. We need fault tolerance, right? That keeps the internet as a whole up. All right, so that is basically this week's lesson. So again, that covers the need for addressing, so IP addresses, DNS, routing, redundancy. Make sure you watch this video because they do a really good job with some visuals of explaining how all this works. So it's good for you to hear it a second time and kind of really get a good grasp on this. All right, so if you have any questions, you can ask me during your check-in. Otherwise, good luck and I'll see you next week.